Hi, in this video I'm going to be presenting the ideas behind the multi-state constraint Kalman filter. My ultimate goal is to demonstrate the code for the multi-state constraint Kalman filter in MATLAB. So before we get to the code, I thought that for the sake of completion and to improve the understanding of the code, it's a good idea to go over the multi-state constraint Kalman filter, because when I was understanding it, it took me a lot of time to figure out what was going on, even though I had an understanding of the Kalman filter. Um, so I thought that for future references and for anyone else interested in the MSCKF, it this could prove to be a good resource. So before we get into the multi-state constraint Kalman filter, it's important that we actually know which parts of the visual inertial odometry pipeline the MSCKF actually tackles. So in a usual VIO system, you would have sensor data which would go into some vision algorithm. This vision algorithm would output feature data and feature mappings, and this would go into some sort of a VIO algorithm like the MSCKF algorithm. Now, in this presentation and in the original MSCKF paper, we're not really concerned with the feature data extraction and the feature mapping, although these are very important parts of an entire VIO system. But in this video and in the actual MSCKF paper, they refer to some techniques, but that is not their major concern. What feature data extraction and feature mapping actually means is that when you have a camera system, you're getting this sequence of images, and what feature data or feature data extraction will do is that it will give you data regarding certain feature. Like, for example, you would detect a plant, it would give you the coordinates in the camera frame, maybe the color, maybe the depth. And what feature mapping does is that it will recognize that same landmark from this frame to a subsequent frame, and then from this frame to another subsequent frame. You will realize why this is important when we get into the MSCKF, because the MSCKF bases its contribution on the fact that you are observing static features in a range of, or a sequence of camera images, meaning that if you have a feature f1, you observe it in frame 1, and then you observe f1 in frame 2, and then you observe f1 in frame 3. These are three consecutive camera frames, and you're observing the same static feature. F1 is a static feature from different camera poses. So frame 1 comes at pose 1, frame 2 comes at pose 2, frame 3 comes at pose 3. So the camera is moving and there is a static feature, and you're observing that static feature from three different camera poses. To detect this feature and to see where it is in subsequent frames, you would need an algorithm that performs this feature data extraction and feature mapping. So an example of such an algorithm would be the SIFT algorithm. There are other algorithms. I can't remember the name of a few of them, but this is an entire area of work in it of itself. Um, there are improvements made in this area by improving the depth estimation, improving the coordinate estimation within the frame, but this is not the concern of the MSCKF algorithm. The primary contribution of the MSCKF algorithm is presenting the measurement model. We'll look at that in this presentation, but I just wanted to point out that this isn't what the MSCKF algorithm is doing, although this is very important. When we get into the implementation, we would be using the KITTI dataset, and we would use a version of the dataset that has already applied this feature extraction and feature mapping, and we would see what we get when we do apply these things when we go into the implementation in detail. Okay, so let's move on with the MSCKF algorithm. So it is a sensor fusion. You are fusing data from the IMU with the camera. So if you're familiar with the Kalman filter, so the IMU is used in the prediction slash propagation slash model based inference. So I don't think inference would be the right word here. What I'm trying to say is that the IMU data in the Kalman filter based sensor fusion fits into the measurement models. Usually in the Kalman filter, when you're not doing sensor fusion, you don't use any data in the measurement models, but in sensor fusion you use the IMU data in the measurement models, and you use the camera data in the update step, or the correction step. These are both names for the same thing. You'll see how that fits in, but generally you're using the IMU data for the in the prediction step, where you use the models for propagation of your system or your state, and the camera goes into the correction step, where you're actually trying to adjust what these predictions were. You're trying to improve these predictions. Like it says here that it's used in the state propagation, while the camera measurements are used to construct the state update for the EKF. We'll see how that is done. But the primary contribution of this paper is the derivation of a measurement model. So in usual Kalman filters, you would have a linear or non-linear measurement model which relates your predictions to sensor measurement. This is what your measurement model does. So what they're saying here is that they found a way, they figured out a way to relate your predictions from the IMU to your camera frames, and we'll see how they're doing that. So we'll briefly go over the IMU measurement based prediction. So this is your state vector. This is the quaternion describing the rotation of the IMU in the global frame. This is the bias in your gyroscope. This is your velocity of IMU in the global frame. This is the bias in your accelerometer, and this is the position of the IMU in the global frame. So this is your state vector, and of course all of these things are vectors in it of themselves. So a 3x1 vector, this would be a 3x1 vector, this would be a 3x1 vector, and you can look up the details for these things in the paper. So these are just the measurement models. So what they are representing is that if how certain things progress in time. So if this is at t in a discrete version of these, if this is at t, this is what the quaternion would be at t plus 1. Of course, when shouldn't be t plus 1, this should be this, as this approaches to 0, because this is the continuous case of these measurement models. But this is what it is actually. So this is how different quantities in the state vector evolve in time. Now, of course, we can't use the these continuous models for evolving the IMU state. So what we do instead is that we use some sort of integration to convert the continuous models into discrete models. Now it's up to the person who's implementing this what kind of integration they want to use. They could use Rankata or simple Euler, and I've seen both of these being used. It's up to you to what degree you want to or to what order you want to apply these integrations. So yeah, and you will find the resulting equations in the original paper and several other papers. So just that this is what we're going to be using the IMU measurements for. So an example would be that this omega t is an IMU measurement. This fits into this measurement model. Yeah, so this is where you would be using the measurements from the IMU, but you would be using them on discrete versions of these equations, and those are not very difficult to figure out. And as is the case, so another thing is that in the Kalman filter you propagate the expectations, you figure out the expectations and you propagate them. So you would figure out the expectations of these equations, and so for example this thing, when you figure out the expectation of this thing, it becomes 0 because this is just a random noise. Similar with this thing, when you figure out the expectation of this thing, it also becomes 0 because you're propagating the expectation. So once you do get the expectations, you would use some sort of integration to figure out the discrete versions of those equations, because you cannot use continuous models. The other thing, in addition to expectations that you propagate in a Kalman filter, from t to t plus 1, you propagate the expectation of the state and the covariance of the state. So this is again figured out through numerical integration. These equations are also available in the paper. So just briefly, this is the covariance of the IMU. This is the cross covariance between the IMU and the camera. This is the covariance of the camera. This is the predicted covariance. And so you first figure this out, and then when you're done with the update step, you will get this. So you would do this with the IMU measurements, and this is what you would get from the update step of the Kalman filter. These are equations, these are the matrices that come from fitting together the entire measurement model. You can find these in the paper as well. Now this is important. So every time you receive an IMU measurement, you update the IMU state vector, and then since you know the orientation and the position of your camera with respect to the IMU, you can figure out the pose, and by pose I mean the position and orientation of the camera through these two equations. So for example, here, let's say you propagated the IMU into this new state which has a quaternion of this thing. You can do this operation, which is, I believe, left quant multiplication, to get this. And similarly, so this C T of I is just the rotation matrix related to the quaternion that propagate the quaternion for the IMUI, which is this one up here. So this is the rotation matrix, and you can figure out the position of the camera and the quaternion of the quaternion of the camera based on your new IMU location or IMU prediction. So again, you would get the IMU predictions. Based on that, you would get new camera pose. So once you do get the new camera pose, you would also need to augment the covariance matrices because these camera poses would be augmented to your state vector. So they also need to be represented in the state covariance. So this is how you would augment your state covariance. So this n here, this n represents total camera poses. So every time you update or have a new number of camera poses augmented to your state, every time the IMU data gives you a prediction, you add a new camera pose based on that new prediction, and then based on that state, you make additions to your covariance matrix. So this would be your entire state vector. This is the IMU state vector we saw earlier, and these are all augmented camera poses, and here you have augmented n camera poses. So these are important as they will play a vital role in the measurement model, and we'll see what that is. Now this is the interesting part of the MSCKF, which is the measurement model and how they've described the measurement model. So this thing is their measurement model. This comes from inverse depth parameterization based interpretation of camera images or features in a camera image. So this was a technique, I believe, that was developed for SLAM, and they're using this sort of representation for features in the camera frame. So let's say that you have a single feature fj that has been observed by a set of camera poses. Now mj is a set of camera poses, so it could be p1, p2, pn, or let's say pmj, and all of them have this feature j in them. That means all of these images, they had a feature j, they had this feature j in them. Now feature j itself could be like a building or a plant or something like that, that this feature, this building or this plant, has been observed in mj camera poses, and these mj camera poses are consecutive camera poses, meaning that these in all of these mj camera poses are just one time frame or camera frame ahead of each other, meaning that this one comes after this one and this one comes after this one, and there is no break in between them, meaning that there was not a pause in between them where feature fj was not observed. So let's say this feature fj was observed by mj camera poses, and each pose is this, it's the position of the camera and the quaternion of the camera. I belongs to sj, which is just saying that it is, so sj would be the set of these camera poses, right? mj is the number of these camera poses, and sj is the set which contains this camera poses. Then the position of this feature j in a camera pose I is represented by this thing. Okay, so this is just the position in ci of fj represented by this thing. This feature position is given in 3 dimension by this, and it can also be written like this. So their contribution begins by using or constructing an optimization problem to get an estimate of this thing, the position, sorry, not this thing, you already have this thing, of this thing, the global position of the feature fj. So what they're essentially going to try to do is that they have a measurement of the position of the feature, right, which is z j I. So this is the measurement of the feature in frame I. If they're able to estimate this thing, right, then they can use this thing to figure out a predicted version of uh, the position of this feature in this camera frame. So this would then become your residual, which would be the difference between the actual measurement and the predicted position of the feature J in camera frame I. So this begins by trying to estimate the global position of the feature. Once you have the global position of the feature, you can figure out the predicted position of the feature, like here. So if you have this thing, you can use this formulation to figure out this thing, and if you have this thing, you can formulate it like this, which would equal to this thing, and that would become your predicted measurement, and the difference of these two things would become the measurement, the residual of your Kalman filter. So again, you would first figure out this thing, you would estimate the global position, and you would do this by using camera poses that observed the feature fj. Once you have this thing, you would use this formulation to figure out this thing, and from this thing you would use this formulation to figure out this thing, which is the predicted position of the feature fj in camera frame ci. And once you have both of these things, this would become your residual, and this is the primary contribution of this paper, that they're able to build this residual. So let's just look at how you do estimate this thing. So you would construct a optimization problem. So let's say that Cn is the camera frame in which the feature fj was observed for the first time. Then the feature coordinates with respect to the camera frame at the ith instant. So what you're trying to do is that you're saying that, okay, I observed this feature for the first time as Cn. How do I translate the position of this feature from that frame to another frame Ci? Now remember that Ci is also a frame where fj was observed. Essentially what you do have is that you have a sequence of frames. Let's call this Cn, Cn plus 1, Cn plus 2, since this was the first frame, Ci, and onward to some, let's call this Cn. This is a sequence of poses where the feature fj sequence, by sequence I mean consecutive sequence of poses, because this is only plus 1 plus 2, where feature fj was observed. For each of these poses we have the position and the quaternion, which would allow us to do this translation of position. And we also have this their relevant measurement of fj. So we have fji, we have zji plus 1, we have zjn, zjn plus 1, and onwards to zjn. So in all of these poses, the feature fj was observed, therefore we have a measurement of the feature fj relevant to each of these poses. So this relates to this pose, this relates to this pose, this relates to this pose, and this relates to this pose. So for each of these poses, we have the position and the quadrangle of the camera. Therefore, for each of these poses, we can do this translation. And for each of these poses, we also have the what should I say? The measurement of the position of the feature in the camera frame. So going forward with this equation, you can write it out as this thing. If you take the zi out of the fj, and then you write it out as this thing, and then you just write it out as this thing, where alpha, beta, and rho, which are these things from here. Okay, so now given these measurements, the ones that we talked about, zjn, zjn plus 1, zjn plus 2, zji, z end. By end I mean the last frame in which the feature fj was observed. By the last frame I mean that after this you received a frame where feature fj was not observed, that at z, at the camera frame end plus 1, fj was not observed, and we would do these updates whenever there is a feature which was observed for some time and then we received a frame where it disappeared. That is when we would go to the update step. Before that, we would always only be doing the IMU predictions, and we would be saving the related measurements and all the camera poses. So you can obtain alpha, beta, and gamma using Gauss-Newton minimization. And how you would do that is that you would set up an optimization problem between this translated coordinates CIPFJ and the actual CIPFJ that you received from your measurements. So you would actually first convert this into the inverse depth parameterization, like here, like this, both of these, because you would be getting the data as a 2D vector, and the 2D vector is the IDP representation of these coordinates. So you would take this, do the IDP, and then you would construct an optimization problem, which is the difference between these two. So I think it would be something like 1 over hi3 alpha j beta j this j into c and zj, this multiplied by I1 and the other two, and you would subtract this from the measurement. You can square this and you would add the other. So you're essentially doing this for all the frames, like I said, for like if this is for CI, this would be this entire same thing for CI plus 1, and this could be the entire same thing for ci plus 2, and you would optimize this entire thing and get an estimate for these three. And once you have this, you can use this thing to calculate this. You can find the details of this in the appendix of the original paper, but to summarize, what you're doing is that you're figuring out all of these positions based on the very first position. So you could do this through triangulation or some other. You could get an initial estimate through triangulation for your optimization, but essentially you're figuring out what, according to this equation, the coordinates of the feature should be when you translate it from the very first pose to these different ci plus 1, ci plus 2 poses are. And then since you have the data related to the feature position for each of these poses, you can set up an optimization problem between the difference of the translated feature position, which would be these things. These would be the translated feature positions, and the actual feature positions which are in the measurements. And from that you could estimate these things. Once you estimate these things, you can estimate this global position of the feature. After doing this, you can again use this, like I said. So now that you have this thing, and this other thing is present in the pose, you can calculate this thing, and you can write it out as this inverse step parameterized formed IDP form, and then you have this residual. So the equations for these, so the rest is just about trying to solve this residual. So the equations for these Jacobians, when you linearize this, because you do linearize stuff in the EKF, are present in the report for the original MSCKF. Now what you do is that you get a residual for each of these, for each of the C n plus 1, ci, c end, as we saw. You stack the residuals. So cj n r j n plus 1 r j I r end, this thing. So you stack them. When you stack them, you call it this thing, and when you stack them, you are also, so this x tilde, this is actually your error state. I didn't mention this because this is just used in the formulation and you can't actually calculate this, so that is why I did not mention this. So once you stack the entire measurement vector, this is what you have. This was earlier, this was xi, but now this is just x and this is just f. Again, the rest is just formulating the residual. So once you have this, you can further formulate the residual by stacking them for all the features, but we'll get to that later. The other problem is that in this feature, in this residual, or in your measurement model, this error state and this position, because the position of the camera is present, or the state is present, or the pose of the camera is present in the in your state vector, there is a correlation between these error state and this feature position, or the error in the feature position, and this is against the assumptions in the extended Kalman filter, or the Kalman filter. In the measurement model, you cannot have correlations between two different terms, and if it is present in the residual model, then therefore it is also present in the measurement model. So you cannot have this. So to do this, what you do is that you take a unitary project this entire thing in the left null space of HF. That does is that removes this term, and you have a more appropriate version of the. So in the actual implementation, we'd be using this part to calculate this residual, because you can't actually calculate these error vectors. So you would find out the null, the projection or the left null space of HF, and you would multiply it with these two stacked measurements and predictions, and that will give you this RO of I. So these are just some summarized or important things of note that the original MSCKF used in the implementation. You can read these up. So they just talk about the maximum number of camera poses that you're carrying and what happens when you go over this maximum number of camera poses. And the other important thing is this that I mentioned earlier: when a feature that has been tracked by a number of images is no longer detected, then all the measurement of the features are processed using the method presented previously. This case occurs most often as features move outside the camera field of view. So we only update when there was a feature that was being consistently tracked, and now you received a frame where that feature was not present. So then you constructed the entire measurement model that we talked about. So this is again when you stack them for all the features. So when you have R of 1, R of 2, R of n for all the features that were not present in this frame. And for better implementations, you take the QR decomposition, and using the QR decomposition, you formulate this final update. And then you just use these R, n, and the covariance that you calculate like this for your Kalman gain, and from the Kalman gain you go to the so this is the delta x, and your update would be x at t plus 1 would be xt plus this delta x, and this is where you would have your updated covariance. And they also share some experiment results, but you can see them in the paper. So I just wanted to share this before I get to the code that I implemented for this. I think that this broadly covers. So I would definitely recommend going through the paper for better understanding, but I think that you would have a broadened idea of what the MSCKF is doing as I went over each step of this. So thank you.